Scientists think there might be a huge onion chilling somewhere out there in space. Not an actual one, but it's something even crazier. These are stars stacked inside each other, layer upon layer. These fascinating objects, called gravastars, could even be cousins of black holes. But most importantly, they might hold the key to understanding some of the most mysterious puzzles in the universe, dark energy, and even other dimensions. Let's start with gravity. Over a century ago, Albert Einstein helped us understand how gravity works. Turns out, it's not just something that pulls things on Earth and makes apples fall on Newton's head. It's much wilder. It's about warping the very fabric of existence itself. Let's say you toss a heavy ball, like a bowling ball, onto the middle of your bed. What happens to the sheets? They dip, don't they? They stretch and sag around the ball. Now, if you roll a smaller ball, like a marble, across the bed, it doesn't move in a straight line anymore. Instead, it starts circling the heavy ball, rolling closer and closer as if the heavy ball is pulling it in. That's gravity. But instead of bed sheets, we're talking about the fabric of space and time itself, or space-time for short. Heavy objects like planets and stars make dents in space-time, and moons, planets, or even light move along these dents. Gravity is the curve that tells them where to go. In that case, you can guess that black holes are like the ultimate heavy balls. The heaviest, in fact. The gravity is so strong, it shrinks them, making them smaller and smaller. So tiny, they could fit in the palm of your hand, but with the mass of several suns. Some of them are like holding over 40 billion solar masses in your palm. It's ridiculous, but they basically create a bottomless pit in space-time with insane gravity. This area around them, called the event horizon, is the most horrifying thing ever. It's a point of no return. Once something gets there, it can never escape being eaten. When something falls past the event horizon, it can't climb back out, not even light. Which is why they seem like, well, black holes. But gravastars, they're something much weirder. Just like black holes, they're probably very compact. But instead of being tiny pits of endless gravity, they might have something wild at their core: dark energy. This is one of the universe's biggest mysteries. Dark energy, this invisible, mysterious something that seems to be pushing the universe apart faster and faster. It's like a polar opposite of gravity. While gravity tries to pull things together to slow down the expansion of the universe, dark energy is trying its hardest to make our world even bigger. Luckily, dark energy has been winning so far. Otherwise, we'd all be in some deep pit. But if we can explain the gravity with balls, then what exactly is dark energy? A force, an energy field. Something else? We have no idea. Scientists have seen its effects. They know that it's incredibly spread out everywhere, but they can't tell you what that thing even is. But if it's trapped inside of gravastars, maybe we'll finally discover the truth. This name stands for gravitational condensate stars. Gravastars were dreamed up by two physics professors, Paul Mazur and Emil Mottola, in 2006. They tried to think what else besides black holes could happen when a massive star collapses on itself. That's how they created this alternative. Think of it this way. Gravity pulls everything inward, making super heavy objects like stars shrink in size. The more the star shrinks, the denser it gets, and its gravity grows stronger. After some point, it can cross a critical threshold and become a black hole. But what if there was dark energy inside to counteract this? At the core of a gravastar, there could be a region filled with false vacuum or dark energy. This energy would push outward, fighting the gravity. It's like the unstoppable force meets an immovable object. Thanks to this, the star core doesn't collapse into a black hole. Sounds wacky. We don't know what dark energy even is, so how can it fill up anything? But luckily, Even if scientists can't fully explain dark energy, they still have strong mathematical models to check how it works in our universe. So, they decided to test this theory. Here's where things get even weirder. The new theory says that gravastars might not be simple lone objects. Instead, they could be stacked one inside another. Each one is like a layer with its own dark energy bubble inside, surrounded by a thin skin of matter. The outermost shell would hold a smaller gravastar inside it, and that one could hold an even smaller one, and so on. It's like a series of balloons, one inside the other. The air pressure in each one of them is stable, evenly spread out. Thanks to that, none of them deflate. They coexist without one popping or collapsing the others. In the case of gravastars, the air is dark energy, and the rubber is the shell of matter surrounding it. It sounds crazy, but it actually makes this whole idea more realistic. A single gravastar might have a very thin shell of matter, but the thicker they are, the more likely it is to exist in a stable way. And finally, the coolest part about them is that they could explain one of the biggest mysteries of our world: how universes are born. When a star collapses into a gravastar, the matter could theoretically implode through the center and create a new dimension. This would connect these objects to the Big Bang itself. Some scientists even speculate that dark energy could be the energy exchanged between our universe and a child universe that's created from a gravastar. Of course, these are all just speculations for now. But where are all those gravastars? And how do we test this? Well, physicists aren't sure either. They're more of a what-if thing than an actual object that they discovered. Those two professors just tried to imagine what would happen if gravity and dark energy worked together like this. For now, the LIGO, a big observatory which detects ripples in spacetime, hasn't found clear evidence of gravastars. Another problem is that gravastars would only be stable in specific cases. For example, if they spin too fast or their shell will be too thick, they might start to wobble or break apart eventually, though it could actually take billions of years. Plus, even if we don't see them right now, remember that this is exactly what happened to the black holes themselves. When Einstein published his groundbreaking theory of general relativity, another scientist, Carl Schwarzschild, took his equations and found a solution to them. And that's when he realized, if gravity becomes incredibly strong, the light wouldn't be able to escape, and this could create a sort of hole in space. Einstein even thought that this sounds too weird to be true. It took many years for us to confirm black holes' existence, and we finally took a photo of one just a couple of years ago. You might remember that blurry picture that blew up online? It was Sagittarius A star, an incredible supermassive black hole in the center of our galaxy, Milky Way. So that's why scientists approach gravastars so seriously. And since all the math checked out, which means that these objects are actually possible in real life. Now, we just need to see if they're somewhere out there. What's interesting is that they'd probably look like regular black holes. They could emit high-energy radiation as they consume matter. They might even produce something called Hawking radiation, a type of energy that escapes from black holes. In other words, it would be nearly impossible to tell the difference. But gravastars have a small trick up their sleeve. If their shell is transparent to light, they might bend light in a slightly different way than black holes do. So maybe if they check the way light is bent around the mysterious object, they could spot the difference. And even if it turns out that gravastars don't exist in our reality, they're still valuable to science. They still taught us more about gravity, black holes, and the limits of relativity. Black holes are massive, the densest objects in the universe. They have such a great mass that their gravitational pull doesn't let anything, even light, escape their clutches. But in this terrifying world of black holes, there are monsters that are in a league of their own. Recently, astronomers discovered a black hole that is 33 billion times as heavy as our Sun. This space giant sits at the center of a supergiant elliptical galaxy called Abell 1201, which is located 2.7 billion light-years away from our planet. This black hole is so large it was given a rare designation, an ultra-massive black hole. No wonder. It's more than 8,000 times heavier than the supermassive black hole at the center of our home Milky Way galaxy. This ultramassive black hole was the first one to be discovered with the help of gravitational lensing. This method is based on the fact that very massive objects such as galaxies bend the light from a more distant object, magnifying it. A great thing about this method of research is that it allows astronomers to study inactive black holes too. It could help us detect loads of new black holes beyond our universe. That's what the area surrounding our galaxy is called. Probably it would help us find some exotic objects we've never seen before. Now, let's speak about another awesome instrument that efficiently helps us explore space, the James Webb Space Telescope. When it stares at young galaxies, which would look like mere red specks to you, it sees an astonishing number of cyclones churning at their centers. Those are black holes. Interestingly, giant black holes were believed to be big players in early cosmic history. But James Webb regularly finds an unexpected number of these beasts. For example, using the telescope, astronomers have detected a supermassive black hole from when our universe was less than 600 million years old. In universe terms, it's just a baby. This is the most distant actively feeding supermassive black hole ever observed. It's located at the heart of its host galaxy called Sears 1019. The black hole is surprisingly small and not massive at all. It's actually one of the smallest found in the early universe. It's equal to approximately 9 million suns. It might sound like a lot, but in reality, supermassive black holes tend to grow to billions of times the mass of our star. There's another unusual thing about this find, and scientists are having a hard time trying to explain it. You see, it's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. The development happens when a black hole either feasts on surrounding matter or merges with a larger black hole. Even black holes similar to the one at the center of our Milky Way galaxy, which is almost 4.3 million times the mass of our Sun, are supposed to be seen in the more recent universe. Actually, scientists have long suspected that supermassive black holes probably existed in the early universe. But this theory has been proven only thanks to the JWST and its infrared eye. It's shown that the black hole Sears 1019 is actively munching on all the matter it can lay its hands on. Such feeding black holes are usually surrounded by swirls of gas and dust, falling inside them, called accretion disks. The gravitational force of a black hole heats this matter, and it makes the disk shine. And that's not all. Extra strong magnetic fields produced in this process channel the matter to the poles of the black hole. From time to time, this matter is released into space in twin, powerful jets. They move at a speed that is close to the speed of light, which generates incredibly bright light. Astronomers were watching the galaxy hosting the unusual old black hole as part of the Cosmic Evolution Early Release Since survey. They saw the galaxy as it was when our 13.8 billion-year-old universe was just 570 million years old. Besides the super old black hole, scientists spotted two other ones. Those probably appeared 1 and 1.1 billion years after the Big Bang. They also discovered 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history. Now, how about having a look at the biggest black holes astronomers have found so far and finding out what would happen to Earth if one of them was to enter the solar system? NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's an elliptical galaxy that has an active nucleus at the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers two symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving towards us. Is it time to pack up and move out of our solar system? The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight-years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. The next black hole is one of the most interesting on our list. It has a mass of 40 billion solar masses and is actually a blazar. It's the most energetic of all quasars, super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun, and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter, about 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of this galaxy, it lies in the mass range of 40 to 100 billion solar masses and emits clear radio signals. But wait for this champion! Astronomers have discovered a gravitational space wonder that has grown to really unimaginable proportions. The black hole I'm talking about is TON 618, and it's a mind-boggling 66 billion solar masses. Yep, we've got another ultra-massive black hole here. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole. And it still won't be enough to create a TON 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You know that black holes are incredibly dense, but it doesn't mean they're some kind of space predators roaming galaxies and munching on everything they come across. TON 618, for example, still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. So the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try and you'll see. And now, what if a supermassive black hole, like the one that dwells at the center of our home Milky Way galaxy, moved a bit closer to our solar system? The answer is simple. We'd be doomed. The distance between this huge thing and Earth would be several dozens of light years, and still, it would wreak total havoc on our planet. Earth, along with other objects making up the solar system, would be tugged into the black hole's orbit and doomed to spin around it for eternity. But you can relax and breathe out. Such massive black holes stay away from us at the moment.
Now really, an object weighing billions of times the mass of our Sun must be easy to find, right? Wrong. Unfortunately, it might not be that simple, like in the case with a missing black hole. But let's travel to the galaxy cluster Abell 2261, hosting a supermassive black hole at its center. Or at least, that's where it's supposed to be. The main problem is this giant space phenomenon is nowhere to be found. Now, supermassive black holes are mega monsters, churning slowly at the center of their home galaxies. They gather tremendous clouds of gas and dust around them, which makes them swell up to sizes the human mind can't begin to imagine. If a supermassive black hole, like the one that dwells at the center of our home Milky Way galaxy, moved even a little bit closer to our solar system, we'd be doomed. The distance between this huge thing and Earth could be several dozens of light years, and still, it would wreak havoc on our planet. Earth, along with other things making up the solar system, would be tugged into the black hole's orbit and doomed to spin around it for eternity or longer. Hey, who knows, right? So, it's good that such black holes stay away from us at the moment. So, let's see what happened to that runaway supermassive black hole from that gigantic cluster of galaxies around 2.7 billion years away from our planet. Scientists have been looking for it with the help of NASA's Chandra X-ray Observatory and Hubble Space Telescope. But so far, no result. The main problem with finding a black hole is that it's, black. And space is, you guessed it, black too. So there's no contrast whatsoever that could help astronomers spot the hole. But scientists haven't given up yet. After all, they have a lot of other technologies to find black holes, small and big, in the vastness of space. Some of these methods involve watching the stars orbiting black holes. Sometimes it's a faint gravitational wave signal which is produced when two black holes collide. But the most reliable technique is watching dust and gas falling to their doom. The thing is, black holes are space objects with insane gravity. So regions of space surrounding them are usually a bit chaotic, gas and dust getting pulled into the bottomless abyss, compressing and heating up. In the process, it releases a flood of X-ray radiation. So, astronomers look for extremely bright X-ray sources in the universe. Chances are those are the last gasps of giant clumps of material before they disappear into a black hole. Then, why can't scientists find such X-ray signatures left by the black hole in Abell 2261? One of the most mysterious things about its disappearance is that radio telescopes have spotted some signs of massive plumes of superheated material launched at one point within the last 50 million years. These plumes were most likely caused by a large black hole, which is nowhere to be found these days. So, at the moment, we can only play a guessing game. Maybe two medium-sized black holes collided, pushing the newly merged giant out of the center of the galaxy. The observations of the stars in that galaxy have shown a clump of dense material a few thousand light-years away from the galaxy's core. Maybe it's the runaway black hole, but disappointingly, no X-ray signals are coming from that clump. Or the hole might still be there in its rightful place, but it's, slumbering. If it doesn't get a fresh supply of gas and dust, it has nothing to feed on. As a result, it can't release a flood of X-rays. But again, the answer, do not disturb, the black hole is sleeping now, isn't very satisfying. Why isn't it getting its space food? What happened 50 million years ago? What is that clump of material speeding away from the galaxy center? So many questions, and no answers so far. At least, we know what black holes look like. Well, kinda. It's actually the shadow of a black hole's event horizon, visible against the glowing superheated material falling inside the hole. The first ever mugshot of a black hole appeared in 2019, but the data for its creation was collected in 2017. It took an international team consisting of more than 200 astronomers 2 years to assemble the image. We can admire this amazing space phenomenon thanks to a vast global network of telescopes called the Event Horizon Telescope Collaboration, or simply EHT. Why such a name? The thing is that the event horizon is a point of no return on the outskirts of a black hole. When something, for example, matter, radiation, or light, reaches this boundary, there is no way for it to escape the black hole's clutches. Anyway, to capture that very first image of a black hole, scientists created a virtual telescope that turned out as big as our planet by combining the power of 8 powerful radio telescopes. But it wasn't an easy feat. The researchers had to simultaneously point the telescopes in a meticulously planned order with the help of precise atomic clocks set on each telescope. Plus, to keep the chances of rain and bad weather to a minimum, they even constructed the telescopes in super dry regions, such as the Atacama Desert in Chile and the South Pole. On each observation day, the telescope gathers roughly 350 terabytes of data. That's 10 times the amount of data collected every day at the Large Hadron Collider. But let's speak more about black holes themselves. There are stellar black holes, smaller but even more dangerous than their supermassive peers. They appear when stars that have run out of their star food fall into themselves. If a star used to be big enough, it keeps compressing and compressing some more, and voila! A baby stellar black hole is born. But even if I call such a hole a small one, it's still 5 to several tens of times heavier than the Sun. Unlike their massive siblings, hypothetical mini black holes could be really tiny, not bigger than an atom. Even so, just one minuscule thing would have the mass of 1,000 SUVs. One theory claims tons of micro black holes could have been created right after the Big Bang and the beginning of the universe. Some scientists even go as far as to say that a couple mini black holes pass through our planet every day. There is a supermassive black hole smack dab in the middle of our galaxy, the Milky Way. Its name is Sagittarius A star, and it's 4.3 million times as heavy as the Sun. And nope, we aren't going to be pulled into this hole. It's more than 26,000 light-years from Earth, too far to have any influence on our planet. By the way, recently, astronomers have discovered that this supermassive black hole might be leaking. If it's true, it probably means that Sagittarius A star isn't a sleeping giant, as previously thought. It might still be active. And the leakage recorded by scientists may be the hole hiccuping while swallowing clouds of gas. Maybe we should burp this baby? If you ever find yourself near a black hole, get ready that time will significantly slow down. It may work for you if you aren't eager to grow older. Just don't let yourself be tugged beyond the point of no return. Another danger of hanging around a black hole is that it might start behaving like a massive galactic volcano. From time to time, black holes flare up, but instead of spewing lava, they produce enormous amounts of energy, and it makes gaping holes in the surrounding material and gas. A short time ago, scientists discovered one of the largest craters in the universe. Radio and X-ray telescopes detected a supermassive black hole that threw a temper tantrum many years ago. It happened in a galaxy cluster about 390 million light-years away from Earth. The crater left behind, which was actually a hole punched in the cluster's hot gas, could fit 15 Milky Way galaxies. Okay, mind blown, I'm out of here.
Black holes are terrifyingly dense space objects, pulling inside everything that comes too close. Nothing can escape their clutches, even a beam of light. At the same time, black holes are some of the most mysterious objects in the universe. According to their mass, black holes are usually divided into 3 categories. Stellar black holes have a mass from a few to hundreds of times the mass of the Sun. Intermediate black holes should range from 100 to hundreds of thousands of times the Sun's mass. Scientists are now actively hunting these missing link black mysteries. But the real behemoths of the cosmos are supermassive black holes. They have hundreds of thousands to billions of times the mass of our Sun. Most supermassive black holes lie in the centers of their home galaxies. You can probably say that they sit in the gravitational driving seat. Meanwhile, hundreds of billions of stars, planets, and moons orbit them. Let's have a look at the biggest black holes astronomers have found so far. NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's actually an elliptical galaxy that has an active nucleus in the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers 2 symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving toward us. The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight-years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. This S5 Theora 1481 is one of the most interesting black holes on our list. It has a mass of 40 billion solar masses and is actually a blazar, the most energetic of all quasars, which are super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter, about 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of IC 1101, it has a mass of 40 to 100 billion solar masses and emits clear radio signals. Recently, astronomers have discovered a gravitational space wonder that is swollen to really unimaginable proportions. The black hole I'm talking about is TON 618, and it's a mind-boggling 66 billion solar masses. The thing is so massive that astronomers had to think of a new term to describe it. They came up with an ultramassive black hole. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole, and it still won't be enough to create a TON 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You probably know that black holes are made of matter packed together as densely as possible. And still, it doesn't mean that black holes are some kind of space predator, roaming galaxies and munching on everything they come across. TON 618 still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. What I want to say is that the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try to do it and you'll see.
Stellar mass and intermediate mass black holes form when huge stars can't support nuclear fusion anymore and collapse, unable to withstand their own gravity. But it's not so clear with supermassive black holes. The mechanism of their formation is still unknown, since there seem to be no stars large enough to directly collapse into such a giant black hole. Nearly every large galaxy has a supermassive black hole at its center, and our Milky Way isn't an exception. We've got Sagittarius A, which is pronounced Sagittarius A star. This space monster is mostly dormant and rarely wakes up to munch on gas and dust, and still, its mass is millions of times that of the Sun. To be precise, almost 4.5 million times. There are still lots of mysteries surrounding this black hole, but one of the most recent discoveries can also be the most exciting. But we'll get there later. Right now, imagine a distance of 14.6 million miles. It's like about 61 distances from Earth to the Moon. That's the diameter of our supermassive black hole. Of course, it will look tiny compared to the Milky Way itself, which is 100,000 light-years wide and 1,000 light-years thick. But it's still impressive. At the same time, Sagittarius A is dwarfed by a disk of gas surrounding it. It extends for a whopping 5 to 30 light-years and occasionally feeds the black hole. When it happens, faint flashes of X-rays are produced. The disk, known as the accretion disk, is also responsible for X-ray emissions triggered by friction. This friction can make the temperatures inside the disk go as high as 18 million degrees F. And now the coolest part, the supermassive black hole at the heart of our galaxy is not just spinning, it's doing so at almost maximum speed, dragging everything close to it along for the ride. Scientists have calculated the rotational speed of Sagittarius A with the help of NASA's Chandra X-ray Observatory. Normally, the spin speed of a black hole is given a value from 0 to 1, with 1 being the highest rotational speed. Speaking of our supermassive black hole, its rotational speed is between 0.84 and 0.96. That's close to the top limit, defined by a black hole's width. Now, the spin of a black hole is very different from that of other space bodies. Solid objects, like planets, moons, or asteroids, have physical surfaces. But black holes are regions of space-time surrounded by an outer, non-physical surface. This surface is called the event horizon, and even light can't escape beyond it. The rotation of a planet or a star depends on the distribution of its mass. At the same time, the rotation of a black hole is governed by its angular momentum. The extreme gravitational forces next to a black hole cause space-time to become slightly curved and twisted. It forms what we know as the ergosphere. This notion is unique to black holes and never occurs around relatively solid space bodies like planets or stars. In other words, when black holes spin, they twist up the very fabric of space-time, dragging along the ergosphere and everything it contains. This phenomenon is known as frame dragging. Come to think of it, the name does make sense. Thanks to this dragging, we can observe weird visual effects around black holes. The theoretical maximum speed of a black hole is determined by how it grows after feeding on matter. As something falls into a black hole, it increases its spin. Plus, we should take into consideration the mass of a black hole. The more massive it is, the higher its gravitational pull is. And this makes it more challenging to increase the speed of the spin. Let me illustrate this idea. Our relatively not-so-heavy supermassive black hole, whose mass is equivalent to around 4.5 million suns, has a spin between 0.84 and 0.96, which is very fast. At the same time, a much heavier supermassive black hole at the heart of galaxy M87, which has a mass of 6.5 billion suns, is spinning just as fast, between 0.89 and 0.91. The solution to this mystery? This black hole is also feeding very rapidly, which allows it to increase its speed.
The James Webb Space Telescope has recently discovered the oldest black hole ever found. It's an ancient monster as massive as 1.6 million suns, and it's lurking 13 billion years in the past at the center of an infant galaxy. This supermassive black hole appeared a mere 440 million years after the beginning of the universe. But it's just one of the countless black holes that inflated to terrifying scales during the dawn of the cosmos. It's the period about 100 million years after the Big Bang. That's when the young universe started to glow for a billion years. This discovery of the universe's oldest black hole can provide astronomers with the answers to some vital questions. For example, how could these space whirlpools balloon in scale so fast after the universe began? Or how did they appear in the first place? You see, black holes in the early universe couldn't grow as quietly and steadily as many modern black holes do. They were bound to experience some peculiar formation and growth. At the same time, closer to the present day, black holes are believed to be born from the collapse of ginormous stars. They grow by munching on gas, dust, stars, and other black holes non-stop. The friction created in the process makes the material, spiraling into a black hole, heat up, and it emits light that can be detected by our telescopes. To spot the oldest black hole, scientists used two infrared cameras, the JWST's mid-infrared instrument and near-infrared camera. They used the camera's built-in spectrographs to break down the light it had been recording into its component frequencies. While examining the results, they discovered unusual spikes among certain frequencies. It could only mean that the hot material around a massive black hole was beaming out faint traces of light. One of the most popular explanations for how ancient black holes grew so rapidly is that they appeared after sudden collapses of colossal gas clouds. Or they could form as a result of merges between clumps of stars and black holes. There's also a possibility that some of the oldest black holes could have been seeded by hypothetical primordial black holes. Those are believed to have appeared moments after the universe began, but their existence hasn't been proven yet. In any case, this most recent finding of the ancient black hole is extremely important because the formation of galaxies and the appearance of black holes go hand in hand. Every normal-sized galaxy that we know of has a black hole at its center. But even though such black holes are massive and can weigh millions and billions of solar masses, they are still tiny in comparison with their home galaxies. A supermassive black hole usually reaches less than 1% of the mass of a regular-sized galaxy and has a volume that is billions of times smaller. And still, somehow, supermassive black holes can influence galaxies, controlling the formation of stars for billions of years. The thing is, black holes exert an enormous gravitational pull on their surroundings. Any gas, dust, and stars that come too close to a black hole find themselves trapped. A lot of material crams into the space around the black hole and heats up, because that's what materials do when compressed. Soon, everything around the black hole flattens into a thin disk, which is called the accretion disk, and starts swirling around the black hole. Astronomers believe that this process is behind the mysterious relationship between black holes and their host galaxies. It's a connection between the mass of the supermassive black hole and the velocity dispersion of the gas in the galactic core. This cycle also controls the rate of star formation, which is a crucial element of the evolution of galaxies. If this delicately balanced process goes off kilter, the outflows from black holes can get too strong, not only heating the gas in a galaxy, but also removing it altogether. And then, the formation of stars doesn't simply slow down, it stops completely. Major galactic merger events can lead to such dramatic consequences because too much material falls into the central black hole too fast.
How about going deep, deep into the past? To the times before humans existed, before the infamous asteroid hit Earth, wiping off 3/4 of life forms on the planet, even before the sun ignited or galaxies appeared in the darkness of the cosmos. So, before light could even shine, there was the Big Bang. It happened 13.8 billion years ago. But what was before that? Some scientists are sure that there was no before. Time started ticking as soon as the Big Bang occurred. We're unlikely to ever figure out what reality was like before that, if any. This is beyond human understanding. But there are those who disagree. Some unconventional scientists theorize that just a moment before the Big Bang, all the energy and mass of the nascent universe could be compacted into an insanely dense but still finite speck. Let's imagine it as a seed of a new universe. And this seed, a chunk of essential material, compressed and hidden in a protective shell, was created nowhere else but inside a black hole. Black holes spin incredibly fast, probably close to the speed of light. Such a spin can give the tightly compacted seed a ginormous amount of torsion. So the seed isn't just tiny and extra heavy, it's also compressed and twisted, which means that it can suddenly unspring with a big bang. Now, let's say you add up the energy and mass of all the particles the visible universe contains. And then you try to figure out the answer to the following question. How big could the event horizon of a black hole with the same mass be? The event horizon is the point of no return. Once you cross this invisible line, there's no way back, even for light. But let's get back to our question. Shockingly, such an event horizon would be very close in size to the actual horizon of the observable universe. There's also this idea that became well known thanks to Stephen Hawking. According to it, every time a black hole appears in our universe, it probably gives rise to a baby universe. But you would only be able to visit such a universe if you crossed the event horizon and plunged inside the black hole. And as you know, once you did it, you wouldn't be able to return. In other words, right now, we might be living in a baby universe. But if some outsider is observing us at the moment, our world looks to them like a regular black hole. So in short, there could be a very old mother universe that forged a seed inside a black hole. This seed had its big bounce all those billions of years ago, and as a result, our universe came into existence. But even though since then it has kept growing and expanding, we might still be hidden behind the event horizon of our home black hole. There's also another idea. According to string theory, there's a multiverse of universes. Imagine our universe as a soap bubble. This bubble keeps expanding, and we live on its surface. String theory claims that our bubble isn't unique. There might be other bubbles out there, and all these bubbles move around, collide, sprout, or bud baby bubbles. In short, live their life. If we follow this theory, we might suppose that black holes are one-way doors between universes. And if you accidentally tumbled down the black hole in our home Milky Way galaxy, you'd end up in another universe. Or rather, not you, but what's left of you after falling through the insane weirdness of the black hole. In this case, this second universe wouldn't be inside ours. It would exist separately, and the black hole would merely be the link connecting them, like a shared route between two aspen trees. Whatever the truth, the danger is still there, lurking in the shadows. What if the black hole we live in decides to collapse? What if it pulls us deeper inside? Or if our world is just a bubble among trillions of other bubbles? What if it bursts one day?
Black holes are the universe's most enigmatic entities. Their voracious nature lets them devour anything close enough, growing in size with each feast. But what's the range of their sizes? Dive in with me. To give birth to a black hole, you need immense gravitational collapse. Typically, this collapse results from massive stars exhausting their life. Imagine condensing the sun to a mere 1.8-mile diameter, or compressing Earth to pea size. What results? An incredibly dense object with immense gravitational pull, a black hole. While we commonly think of colossal black holes, tiny ones might exist. Known theoretically as primordial black holes, they could be minuscule, down to atomic dimensions. These ancient entities might predate even atoms, originating just post the Big Bang. Back then, with the universe in a tumultuous state, even a slightly denser particle might have become a black hole. These atom-sized black holes might weigh as much as mountains, while those weighing like Earth might only be coin-sized. Though fascinating, their lifespan would be brief due to extreme temperatures making them evaporate swiftly. Our universe houses the known category, stellar black holes. Their mass is often multiple times that of the Sun. For context, the Sun's weight is a mind-boggling number with 30 zeros. The smallest recognized black hole is 2, 4 times the Sun's weight. It drifts through space, hunting for cosmic prey. Gaia BH1 is our nearest neighbor, with 10 times the Sun's mass. At a staggering distance, M33X7, some 3 million light-years away, currently consumes a blue giant far bigger than the Sun. Transitioning to larger ones, we find intermediate mass black holes. They achieve their size by either consuming numerous stars or frequently merging with other black holes. A prominent example weighed 142 solar masses, overshadowing some earthly regions. A pair was recently spotted in a galaxy 17 billion light-years away. Though they'll eventually merge, their current interaction unleashes enormous energy. But the true behemoths in this category are the supermassive black holes. These cosmic giants have masses millions or even billions of times greater than the Sun. The colossal nature of supermassive black holes is baffling. How did they grow so immense in a universe that's only 14 billion years old? Enter quasi-stars, hypothetical stellar titans that dwarf even the largest known stars, like Stephenson 2.18. These could have birthed from the universe's early days, with cores collapsing into black holes even before fully forming. Inside a quasi-star, its newborn black hole would feed on the star's matter, growing larger while maintaining the star's equilibrium. Over millions of years, the black hole would swell, resulting in the supermassive black holes often found at galaxy centers. Contrary to belief, galaxies don't orbit these giants. For instance, our Milky Way's heart houses Sagittarius A, a 4 million solar mass black hole, just 17 times the Sun's size. However, not all black holes are dormant. The one in BL Lacertae gobbles up vast quantities of gas and dust. Then there's the black hole in Messier 87, captured in humanity's first black hole image, capable of swallowing our solar system up to the Orion Belt. But the universe harbors even grander entities, ultramassive black holes. These monsters outshine thousands of galaxies, drawing in everything in their vicinity. OJ 287 Center features one weighing 18 billion solar masses, so vast another black hole orbits it. Lastly, meet TON 618, the universe's largest known object, with a mass surpassing 66 billion suns. Its brightness exceeds 100 trillion stars, illuminating even from 18 billion light-years away. The enigma? We're observing TON 618 from 10 billion years ago. Its current size remains an awe-inspiring mystery, likely magnitudes larger than our last glimpse.
If you somehow fell into a black hole, it might change your future and erase your past. Well, at least theoretically. Let's start with the real world we live in. Here on planet Earth, your past can definitely define your future. But imagine you're not on Earth, but somewhere out there in the endless universe, and you stumble upon a certain type of black hole. The one that a UC Berkeley mathematician found. Not to mix it with a regular black hole, let's call this type, what about a benign black hole, huh? So here's why you need a specific black hole. Thing is, you're highly unlikely to stay alive in a regular black hole. But according to some calculations made by a postdoctoral fellow, Hinz, from UC Berkeley, this specific type of black holes we agree to call benign ones might expand at an accelerating rate. This is what makes it possible to survive the transition from our deterministic world to a black hole, which is not deterministic. Let's imagine you survived that passage, and now you're moving towards the center of a benign black hole. It's impossible to picture what's inside, and if you, as a traveler, could actually get into a black hole, you'd never be able to communicate to the outer world what interesting things are hidden in it. But it's not what interests us for now. We need to know how to get rid of the past. Hinz, the mathematician you already know, studies non-rotating black holes that have an electric charge. The most important thing about them is that besides the event horizon, they also have the Cauchy horizon. And here's the point. The Cauchy horizon is the place where so-called determinism simply breaks down. This may sound too scientific, but let me explain it to you. The Cauchy horizon is the place where your past doesn't determine your future any longer. So, here's a mathematically proven and apparently working method of how to get rid of your past. All you need to do is get into space, find a specific black hole, make it to the center, and get to the Cauchy horizon. However, if it sounds too complicated, you can simply try not to make mistakes here on Earth. Yeah, ideas like your past gets cancelled, you have an infinite amount of options of how your future will evolve, and all that jazz sounds as unrealistic as they are appealing. Like, imagine no one knows you failed to get into college and get a degree, but from now on, you have every opportunity to do whatever you want. But only theoretically. In reality, once you get into the black hole, not that specific one we've already talked about, you're most likely to disappear once and for all. But hey, don't be sad. I'm only talking about your current physical form. It's a bit deeper than it might seem. Thing is, there's a curious principle of quantum mechanics that can be explained in a simple way. For starters, imagine that you're not a human being, but just information. You have your experience, your background, and your thoughts. All of these are the information you are. Now, let's make it even simpler. Imagine a USB drive or a book. Both of these things contain information. If you smash a USB drive that contains music and movies, it won't exist anymore in its physical form. but the information it had will never stop existing. Same with the book. If you burn it, the information it has doesn't get burned. It continues to exist, but in another form. So, this fun theory claims that even though someone passes the horizon of events, which is a point of no return before you get spaghettified, they don't stop existing. In simple words, these universe travelers still exist, but in the form of information. Now let's go back to the black holes. According to Stephen Hawking, black holes emit radiation. Radiation makes them shrink, and with time, I mean much time, a black hole can shrink so much that it eventually disappears. So what happens to the astronaut who got entangled in a black hole if it disappears? Nope, they won't be ejected from the black hole in the way they used to exist. However, they will still be ejected from there, but in the form of Hawking radiation. But it's just a theory. Right, you remember that no one knows exactly what happens in the black hole? Another theory says that what happens in the black hole doesn't really stay in the black hole. Sounds like a good alternative to Las Vegas if all the flights for the weekends have been booked. Some scientists believe that a black hole might have a portal where you can turn back time. According to this theory, there's a white hole at the end of a black hole. If you get there, you can undo things. Like, you broke your mom's favorite vase? Hop into the white hole and it'll be as good as new there. You cooked a scramble and made a fresh orange juice, but somehow lost your appetite. It's not a problem if you cook it inside a white hole. Voila! The eggs are unbroken. The oranges are uncut and juicy again. No more food waste. Alright, turning back time sounds really cool, so I guess we might actually need a black hole to help us out. If a black hole was made in a, let's say, lab, it could devour things until it grew big enough to consume the entire planet. First, it would munch on the Large Hadron Collider, which might possibly create something similar to a black hole here on Earth. Next, Geneva, where the Large Hadron Collider is located. Then the whole country of Switzerland, then Europe. At that point, it wouldn't be long before the Earth was gone too. Luckily, if a black hole did appear, it would be so small that it wouldn't be able to do anything. Black holes actually produce a lot of energy and release it, often as heat, like a furnace. That means they will fade away when they run out of fuel. Even if a stable microscopic black hole was created, it would grow so slowly that nothing would happen. Assuming that it survived long enough to absorb the tiny particles around it, a black hole of this size would take super long to get even a pound of weight. I won't be around then. But a black hole on Earth could be a great thing. Even a relatively small one may emit enough energy to completely power humanity. We're talking a lot about food, huh? Let's not forget about spaghettification. The concept is quite simple, by the way. It's all about gravity. Imagine you're playing with chewing gum. With your force, you can easily stretch it so instead of a regular piece, you can get a long and thin one. The same happens to you. Black hole force is enough to stretch you as if you were a piece of chewing gum. Gravity holds you tight on one side, which makes you stretch. You may wonder, how come you don't get spaghettified on Earth if there's gravity too? Easy peasy. It's just too weak to do that with you. If you asked a butterfly to stretch the gum, would it be able to do that? Not likely. Their tiny limbs are just too weak. Same here. The Earth is just too weak compared to a black hole. So, if you were wondering whether you'll ever reach 6'6", it may never happen on Earth. But once you're in a black hole, you can go far beyond those mere 6'6 inches. Your best height moment won't last long though. If you stretch the chewing gum at one moment, it will simply tear apart. The same will happen to you because of spaghettification.
For a few decades, scientists have been debating whether there's a mass gap between the heaviest neutron stars and the lightest black holes. And finally, for the first time ever, researchers have discovered an object with a mass falling right into this gap. It started on the 29th of May, 2023. The LIGO Livingston detector in Louisiana recorded a mysterious signal. It was produced in the process of a merger of a neutron star with an unknown compact object. It was most likely an unexpectedly lightweight black hole. Its mass could be just a few times that of our Sun. That's why this object falls into the lower mass gap between the lightest black holes and the most massive neutron stars. According to Einstein's theory of general relativity, neutron stars are likely to be lighter than 3 times the mass of our Sun. But the exact mass after which a neutron star will collapse into a black hole is still unknown. And considering our previous electromagnetic observations, we can expect to find very few black holes or neutron stars within the range of 3 to 5 solar masses. And still, the mass of one of the newly discovered objects perfectly aligns with this range. But let's have a better look at how the situation with the LIGO detector unfolded. Just 5 days after the launch of the 4th observing run, things became really exciting as the detector recorded a gravitational wave that was classified as signal candidate S230529A. The online analysis was performed almost in real time as the signal arrived. And the conclusion was astounding. A neutron star and a black hole most likely merged around 650 million light-years away from our planet. Unfortunately, it's impossible to say exactly where the merger had occurred since only one gravitational wave detector was recording scientific data when the signal arrived. That's why the direction from which the gravitational waves came wasn't determined. And still, the researchers were sure that the signal wasn't some local disturbance in the LIGO Livingston detector. It actually came from deep space. To figure out the properties of the space bodies that orbited each other before merging and producing the gravitational wave signal, astronomers compared data from the LIGO Livingston detector with 2 waveform models. The detected signal appeared as a result of the merger of a compact object with 1.3 to 2.1 times the mass of the Sun, and another compact object with 2.6 to 4.7 times the Sun's mass. Were these compact objects a neutron star and a black hole? We can't tell for sure using gravitational wave analysis alone. But based on everything we've learned about the properties of this binary, astronomers think that the lighter object is a neutron star and the heavier is a black hole. Of all the neutron star-black hole mergers we've detected so far, the most recent one is also the one in which the masses of the 2 participating objects are the least different. Experts explain that if a black hole is way heavier than a neutron star, no matter will be left outside the black hole after the merger. No electromagnetic radiation will be emitted either. As for lighter black holes, they can rip neutron stars apart with their strong tidal forces. In the process, they eject matter that might glow as a kilonova or a gamma-ray burst. The detection of this interesting phenomenon became possible due to several improvements made to the detectors, which increased the sensitivity of the equipment. The highly successful 3rd observing round finished in spring 2020 and brought the number of known gravitational wave events to 90. The 4th observing round started in May 2023. Researchers at an institute in Hanover, together with their LIGO colleagues, have improved the laser sources of the LIGO detectors located at the heart of the instruments. Along with hardware, experts have also worked on other features of the detector. And now, these space exploration tools can figure out the properties of black holes within mere days.
Dark, ever-hungry monsters live all across the universe. They're born when massive stars blast into space. Black holes, as heavy as Earth, are just as large as a ping-pong ball. They don't have a surface, but their gravity is so strong even light can't escape it. Black holes don't have physical boundaries like a membrane either. The event horizon, which is closest to a typical boundary, is a threshold which, after passing, you can't get out. For a star, running into a black hole normally ends in a spectacular light show and its destruction. Just one star that astronomers know of managed to survive an encounter with a black hole as heavy as 400,000 suns. It happened in a galaxy about 250 million light-years away from Earth. Astronomers with really powerful equipment noticed bursts of X-rays that raged in space every 9 hours. They thought they must be mayday signals from a star trapped by a cosmic abyss. The star was an average red giant when it met its new friend for the first time. When they got too close to each other, the hungry space monster couldn't resist the temptation and snacked on its guest. When it was done with the star's outer hydrogen layers, all that was left was the star's core. Eventually, the poor thing turned into a white dwarf. But for some reason, the giant space monster couldn't finish the meal and trapped it in its orbit for later instead. Ever since, the now white dwarf has been traveling in 9-hour laps. It stays far enough from the hole so it won't fall in or get swallowed. Its journey isn't going super smoothly. Because of gravity, the orbital path is constantly rotating. After 2 days, it resembles a spirograph pattern. As the black hole keeps snacking on it, the star keeps losing its mass and growing in size. Its own orbit is becoming more and more circular. Scientists believe one day it will be able to spiral away from its mean friend and turn into a planet the size of Jupiter in 1 trillion years. That's 70 times longer than the universe has existed so far, so it might not ever happen. The Milky Way alone has hundreds of millions of black holes, and there are way more beyond it. They might feed on other stars and release them in other galaxies. The telescopes that exist now might not be strong enough to spot them. Most galaxies, including our Milky Way, have supermassive black holes at the center. They can be billions of times heavier than the Sun. Others of their kind are only 3 times the mass of the Sun. The nearest black hole to the Earth was spotted 1,000 light-years away, just around the corner in galactic terms. It's in a star system you can see with an unaided eye. Scientists found it when they noticed a star behaving weirdly. It was a giant, rotating like crazy. They guessed it must have a powerful gravitational companion. The hungriest black hole astronomers have spotted so far weighs as much as 34 billion suns and is about 6 times bigger than the one at the center of the Milky Way. It eats the equivalent of 1 sun every day. Sometimes black holes even devour others of their kind that happen to be too close to them. Before you get on a spaceship to escape to some safe, no black hole galaxy, here's some good news. Even though they're supermassive, they don't have a radius large enough to destroy Earth. And even the hungriest of them are safe to watch from a distance. No black hole should come closer to our planet than the Sun for as long as the universe has existed, multiplied by 10 billion times. In the unlikely case one of these scary things passes by Neptune, it could affect the Earth's orbit. That would be no good. In theory, anything can turn into a black hole. The only difference between it and the Sun is the material their centers are made of. It's incredibly dense in those huge space monsters. In reality, there's just one known way to make a black hole. It has to be the gravitational collapse of a supermassive star, 20 to 30 times the mass of the Sun. So, the Sun will never ever become a black hole. If it happened, though, and the former star retained its mass, it would still have the same gravitational power. Earth would still keep going around it and wouldn't get pulled in. Its orbit would also remain as it is. The only huge problem would be the lack of sunlight. In reality, the Sun isn't massive enough for such a transformation and will eventually become a white dwarf. A black hole won't ever eat an entire galaxy for lunch. There are about 400 billion stars inside the Milky Way. Just around 0.1% of all the stars that will ever form will end up becoming black holes. The ever-hungry supermassive monster, located right in the middle of a galaxy, has an impressive gravitational reach. But even that wouldn't be enough. It has already eaten most of the stars that were close to it. It already weighs like a few million suns, so it can't grow much larger even if it keeps snacking on sun-like stars. Galaxies will keep bumping into each other, and black holes will keep growing and merging. But because the universe is already huge and keeps expanding, these collisions and mergers won't go on forever. Black holes will travel this huge space like rogue stars. They won't even be able to eat the dark matter on the outskirts of galaxies. Eventually, all the black holes will perish, but that would be a long, long time from now. If you ever become a space explorer and travel far enough to meet a black hole and fall into one, your life won't instantly end. Instead, things will be way more complicated. The way you perceive space and time will change, and your reality will split in two. In one of them, you'd cease existing. In the other, you'd live and enter the hole unharmed. When you go deeper inside the hole, you'll notice space becoming curvier and curvier. At the center of the hole, it's infinitely curved. It's called singularity. Laws of physics based on the ideas of space and time don't have power here. In a large enough hole, millions of times more massive than the Sun, things would go perfectly smoothly for you. And you just keep free-falling, feeling no gravity. You could just keep falling and falling in total emptiness until you reach singularity. You'd have no chance to move in the opposite direction. In there, space and time switch roles. Time is constantly pulling you forward on Earth, but figuratively, and it would be doing that quite physically inside the hole. In a smaller hole, the force of gravity would be stronger at your feet than your head. That's why you would go through spaghettification. This is how scientists call the process when you compress horizontally and stretch vertically like spaghetti because of crazy gravity of the black hole. Speaking of spaghetti, how are black holes like an Italian dinner? Because once you go past the event horizon, you get spaghettified, and since you're all by yourself, you'd be feeling cannelloni right now. Wow, now I'm hungry. Meanwhile, if you had a fellow space traveler who, for some reason, didn't end up in the black hole, it would look all different to them. They'd see you stretch and grow, like through a huge magnifying glass. The closer you get to the edge of the hole, the more it would seem like you're moving in slow motion. Then you'd freeze, and the flames would surround you. You'd be in two places at the same time, living different destinies, but there would still be just one copy of you. This is how black holes teach us nothing is real. Reality can be different to different people. Some scientists believe that we're all living inside a huge black hole. Everything in the universe started with the Big Bang. But there's a theory saying there was also something before that. It was a super dense seed that had all the mass and energy of the universe concentrated in it, about as heavy as 1 billion suns. It was 1 trillion times smaller than any particle humans can observe. This seed could be born inside a black hole. If you believe there's more than one universe, black holes could also serve as doors between those universes. It could be like a root that two trees share. You can't see a black hole directly because it doesn't give off any light. Scientists used to be able to only spot them by what they were doing to their surroundings. When over 200 scientists around the world worked together, they managed to take the first pictures of that space oddity. The equipment they used, added together, would be the power of a telescope the size of Earth.
Black holes, an enigma that has puzzled scientists and captivated our imagination for decades. But what's hiding inside of a black hole? Is it a void? A bottomless pit? A parallel universe? We don't know for sure yet, but scientists might have some ideas. So let's hear them out. Picture this. In the vastness of space, there's a supermassive star, shining bright like a diamond. But like all good things, this star's party can't last forever. Eventually, it runs out of fuel and goes out with a bang. Quite literally, the star collapses under its own gravity, creating an implosion. Now, this collapse is so intense that it creates a bottomless pit in space, like a sinkhole. This is what we call a black hole.
the ultimate no-escape zone, sucking up everything in its vicinity, including light. Imagine yourself approaching a black hole. The black hole itself doesn't emit any light, but you can notice a dazzling display of cosmic fireworks surrounding it, the accretion disk. It's like a celestial carousel of gas and dust swirling in a mesmerizing dance around the black hole. The incredible gravitational forces pull all this material from their surroundings, creating this celestial furnace. Of course, it's very unlikely that you would have survived in this place. Temperatures here soar to millions of degrees. Also, it's constantly dazzling X-rays and high-energy radiation that can be detected from telescopes on Earth. But let's imagine that you did survive, somehow. As you get closer, you notice a mysterious boundary looming ahead, the event horizon. It's a point of no return, beyond which the laws of physics seem to go haywire. Now you're stuck in a space traffic jam, and no matter how hard you hit the gas, you're going nowhere. Once you cross this threshold, not even light can escape. And now, you inevitably fall into a black hole. What do you see around you? According to the genius physicist Albert Einstein, space and time aren't separate entities, but rather intertwined in a fabric called space-time. It's like a cosmic trampoline that can stretch and bend if you place something heavy on it. And black holes are super heavy, which is why they distort this trampoline in the most extreme way possible. So when you venture close to a black hole, you're in for a roller coaster ride. The curvature of space-time becomes so intense that it's like a whirlpool pulling everything in, even light itself. Everything around you looks like a space funhouse with distorted colors and rays of light that keep shifting. All this makes you feel like you're doing the moonwalk on a treadmill. Also, the curvature of space-time around a black hole is so extreme that it creates a phenomenon called time dilation. Time near a black hole moves at a different pace than in the rest of the universe. The closer you are to the black hole, the slower time ticks, like a slow motion effect. And the deeper you fall, the weirder things get. The laws of physics seem to break down before your very eyes. But suppose you somehow manage to survive all this madness. Where exactly are you falling? What awaits you on the other side? Is there even an other side? As you venture deeper into the celestial maelstrom, you reach an elusive and mysterious point called the singularity. It's the heart of a black hole, a place where all matter and energy are crushed into a single, unimaginably dense point. Imagine cramming masses of entire stars to something that is essentially a pinprick. And now that you're here, forget about the usual rules of physics. Welcome to a new realm, where the known breaks down and the unknown takes over. So, what does this unknown look like? Well, there are a couple of theories. First off, it could be a gateway to other dimensions. What if there are multiple universes hiding within black holes, like nesting dolls? According to this theory, the interior of a black hole could be a portal to a parallel universe with its own set of physical laws and possibilities. This parallel universe could be drastically different from our own world. What a mind-bending idea! Or what about wormholes? Imagine black holes forming a space subway system, connecting different regions of space and time with each other. These theories suggest that the extreme gravitational pull of a black hole could create a wormhole, a tunnel that could transport you to another galaxy, or even to the past or future. It's like finding a secret passage in a video game. That's not all. Some scientists propose that inside a black hole, we might find some exotic matter, some strange matter with weird properties or negative energy density. If that's the case, this would defy our understanding of the universe. And finally, one of the most mind-bending theories is that a black hole could actually lead to a white hole. Imagine, as you fall further, you suddenly find yourself in a blindingly bright space show. You're in a white hole. This is a fountain that's spewing out matter, energy, and information into the universe with reckless abandon. The birthplace of new universes. You see, while black holes are known for their event horizon, white holes have an anti-event horizon. With black holes, everything can enter and nothing can come out. With white holes, it's the other way around. They repel everything. White holes are hypothetical objects. Their existence hasn't yet been proven. But if it turns out that they exist, they could be connected to black holes. It makes sense. Black holes suck everything in, and white holes should take their matter from somewhere. And all this matter and energy coming out of the white hole could potentially form new universes. Together with black holes, they could form a universal cycle of creation. The end of one universe leads to the birth of another. All these theories are beautiful and fascinating, but here's the catch. There's still no concrete evidence of any of them. Black holes still remain one of the biggest mysteries of our world. Unfortunately, studying these mysterious beasts isn't easy. They're super elusive, and this is one of the biggest challenges for scientists. Black holes don't emit light, so they can't be seen directly. They're essentially invisible to telescopes that rely on light, making them incredibly difficult to observe. That's why scientists have to rely on things like X-ray emissions, the effects of a black hole's gravity on nearby objects, and other clues. They're also very unpredictable. For black holes, physics is like a fun playground. They warp space and time around them, which makes it difficult to predict and understand their behavior. But don't worry, space enthusiasts. The future of research in this field is as promising as ever. We've already made incredible discoveries. For example, in 2019, we captured the first ever direct image of a black hole. This is a central black hole of the galaxy Messier 87. A few years later, we also took a photo of a black hole in the center of our own galaxy, the Milky Way. This one is called Sagittarius A star. All this has opened up new avenues for research. And these aren't the only cool things we've discovered in recent years. Let's take gravitational waves, for example. You know how rocks leave ripples after falling into water? Well, gravitational waves are ripples in the fabric of space-time. They carry clues about the most cataclysmic events in the universe. They've allowed us to listen to the universe, unveiling previously hidden phenomena and events. And all these observations provide us with a new way to study black holes. We constantly make new advancements in technology. The James Webb Space Telescope will provide us with even more detailed observations and insights into the mysteries of black holes. There's still so much we don't know, but that's the beauty of science, the thrill of the unknown, and the curiosity that drives us to explore the mysteries of the universe. So, let's keep peering into the cosmic abyss on the thrilling quest to unlock the secrets of our world.
Imagine a being so powerful it can suck in entire galaxies, so mysterious it's invisible to the naked eye, and so impressive it bends the very fabric of space and time to its will. Yes, meet my mother. Just kidding. Actually, meet the ultimate superhero of the universe, the black hole star. What is it and how does it work? Well, let's find out. The universe is full of marvels, and the black hole star is one of the most impressive ones. It's a supermassive force that can bend the laws of physics and a true enigma for scientists to unravel. No wonder science fiction writers find them so captivating. A black hole star, also known as a quasi-star, is a hypothetical type of extremely massive and luminous star that may have existed early in the history of the galaxy. They're predicted to be as luminous as a small galaxy, But unlike modern stars, they weren't powered by nuclear fusion in their cores. A quasi-star's energy would come from material falling into a black hole at its core. And yes, just like a normal black hole, these stars have the power to suck in anything and everything that gets too close, including stars, dust, and even entire galaxies. But how is it possible that the star is born from a black hole? And what's more, how do they continue to coexist together? Well, first let's discuss how black holes are born in general. It all starts with a supermassive star, one that is at least a few times more massive than our own Sun. This giant of a star burns bright and hot, shining with the light of 1,000,000 suns. But eventually, it runs out of fuel and its fate is sealed. As its lifespan comes to an end, it makes one final massive boom, a blast so powerful it can outshine an entire galaxy. This blast is called supernova. During this boom, the outer layers of the star fly away, while the core gets squished together by its own gravity. If the squished core is heavy enough, it can keep squishing until it becomes a black hole. And just like that, a black hole is born. Don't even try to put diapers on this thing. Now, this cosmic monster baby can continue to grow by swallowing up anything that comes too close, including stars, dust, and even entire galaxies. This is basically what's happening now in our universe with supermassive stars. But what about quasi-stars? The formation of a quasi-star could only happen early in the development of the universe, before hydrogen and helium were contaminated by heavier elements. And because of that, quasi-stars have one important feature. They are gigantic, so enormous that it's literally impossible to imagine. They may have been dwarfing even the largest known modern stars, like VY Canis Majoris and Stephenson 218. No wonder they're so scary. They were born from protostars, one of the first stars in the universe, the great-great-grandfathers of, everything. So now imagine a protostar so massive that its core collapses into a black hole, just like we described before. But the key difference is that in a regular supernova, the outer layers of the star are blown away by the energy released during the boom. Meanwhile, in a quasi-star, these outer layers are massive enough to absorb the energy without being blown away. What do we get in the end? A star with a black hole in its core that weighs from 1,000 to 10,000 solar masses. This quasi-star is about 14,000 times bigger than our Sun, which makes them bigger than any star we know today. These celestial titans have some pretty crazy properties. Once a black hole is formed at the center of a giant protostar, it starts to give off a ton of energy. This energy helps to balance out the force of gravity, making it kind of a giant fusion-based star. They would be so bright that each one would look like a small galaxy. Quasi-stars would have a pretty short lifespan, around 7 million years. Just for comparison, our Sun is about 4.5 billion years old, and it's only halfway through its lifetime. But either way, during this short period, the black hole at the center would grow to be about 1,000 to 10,000 times the size of our Sun. Quasi-stars are also thought to be super hot, with temperatures reaching over 17,500 degrees. But as a quasi-star gets older, it starts to cool down, and its outer layers become see-through. Eventually, it cools down to a temperature of 6,740 degrees, and at that point, it's curtains for the quasi-star. It can't survive at that temperature, so it just dissipates, leaving behind an intermediate mass black hole. Unfortunately, right now, there's no observational evidence for the existence of quasi-stars. This is because they're thought to have only existed a very, very long time ago. They may have been very massive population 3 stars, which are extremely rare and difficult to detect. It's also very unlikely that any of them would still exist today because of their super short lifespan, only 7 million years. So why do scientists believe that quasi-stars could have existed? Because they're looking for ways to explain how supermassive black holes formed so early in the history of the universe. They're found at the center of most galaxies. But how could these monsters have formed so quickly? After all, it takes a really long time for small black holes to grow into supermassive ones. This is where the idea of quasi-stars come in. These stars aren't just destructive forces of nature, they're like the black belts in the martial art of gravity. They can bend and twist anything to its will. That's why these stars, if they really existed, had to play a crucial role in the evolution of galaxies. They must have been instrumental in shaping the universe as we know it. So, those intermediate-sized black holes that they left behind could eventually turn into supermassive black holes in the center of galaxies. But we're still yet to solve this cosmic mystery. Detection and study of black hole stars is like trying to find a needle in a haystack. Only instead of a needle, it's an invisible and mysterious object. And instead of a haystack, it's the vast expanse of space. But with the help of some pretty cool technology and a lot of brainpower, scientists are getting closer to uncovering the secrets of these celestial giants. Here are some things that can help us in this research. First of all, gravitational waves. They're like ripples in the fabric of space-time, caused by the movement of massive objects. Albert Einstein predicted them way back in the 20th century, but they were finally detected only in 2015. We caught them by observing the collision of two black holes. This discovery confirmed that black holes can merge and that they're a powerful source of gravitational waves. Scientists think that by studying these waves, they can learn more about how black holes form and grow. We can also try to detect quasi-stars by observing the effects of their gravity on nearby objects. It's like trying to spot a criminal by their fingerprints. For example, if a black hole is located near a star, scientists can observe the star's light being distorted as it's pulled toward the black hole. And of course, we can use our technologies, such as X-ray, infrared, and radio telescopes. This allows us to study black holes in various ways and at different stages of their lives. In other words, scientists are working hard to uncover the secrets of these celestial giants. We develop new telescopes, search for primordial black holes, and try to understand the connection between black hole stars and dark matter. And we're making some pretty incredible discoveries, just like with gravitational waves. All these things will bring us closer to uncovering the secrets of quasi-stars. And when we find out the truth about them, it will become a new page in our scientific history.